measurements might seem extremely straightforward, as practically all our activities are influenced by them. When we buy food, someone has weighed it and we pay according to the result of that measurement. Even our state of health depends on how some of our parameters have been measured. We might therefore think that metrology, that is, the science of measurement and its applications, is concerned only with designing and using measurement methods and instruments in the best possible way. That's true, but it's not the whole story. Metrology also has the equally important task of ensuring the quality of the provided results, that is, how well they succeed in representing the quantity being measured, known as the measurand. We can sense that due to the many imperfections affecting measurement procedures, we are not able to know the true value of the measurand. We must therefore be able to assess how close we get to the true value, or, if you prefer, how well we measure. So, this is the important task of metrology, and the ways in which it is carried out are independent of the quantity being measured and the context in which the measurement takes place. And this is precisely what we will be dealing with in this course. Let's see how. Now, first of all, we need to learn how to use the typical terms and concepts of metrology correctly. The international vocabulary of metrology, known as the VIM, helps us with this. You can download it for free from the BIPM website, which is the Bureau International de Poids et Mesures, the international organization that governs metrology. And the VIM has been incorporated into the international standard ISO IEC Guide 99. Let's start with the definition of measurement. Process of experimentally obtaining one or more quantity values that can reasonably be attributed to a quantity. First of all, you can see that this is an experimental activity. Furthermore, the definition refers to multiple values, immediately making it clear that a single value is not enough to know the measurand. Now, let's see how the VIM defines a quantity. Property of a phenomenon, body or substance, where the property has a magnitude that can be expressed as a number and a reference. A reference can be a measurement unit, for example, a length of 1 meter, a measurement procedure, such as the Rockwell C hardness, which defines a procedure for measuring the hardness of a material, or a reference material used in the measurement of chemical quantities. Let us now ask ourselves whether a number and a reference may represent a measurement result. For example, if we say that the table is 1.6 meters long, is this a measurement result? Let us see how the VIM defines the measurement result. Set of a quantity values being attributed to a measurand together with any other available and relevant information. And here the concept of a set of values comes back together with the need to have further information, which, as we will see, helps us to understand how these values are distributed about the true value of the measurand, which, let's never forget this, we cannot determine. We will see later on that this further information is called measurement uncertainty. Let us now try to understand how a measurement result is obtained and what processes we must follow to get it. We have seen that to measure means to assign values to a quantity, that is, to a property of a phenomenon, body, or substance. So, what is a property? It is an empirical concept. A length, a mass, an electric current manifest themselves in the empirical world of facts, events, occurrences. And what is, then, the value that we assign to a quantity? We have seen that it consists of a number and a reference. And what are them? They are symbols that belong to the world of abstractions. To measure, therefore, means to build a bridge between these two worlds by identifying a series of processes that allow us to map a manifestation Q of a property onto a symbol X. Let's look at this in mathematical terms. Once the property Q and its manifestations Q1, Q2 up to Qn have been defined, and the class of symbols X has been established, the mapping process is written like this or like this. However, let's pay attention to a point. This process is not a one-to-one mapping. In fact, it is possible to have manifestations of the same property that are different, though undistinguishable, due to the imperfections in the measurement process, and are therefore mapped onto the same symbol. For the same reason, for example, due to accidental disturbances, it may happen that the same manifestation of a property is mapped onto different symbols in repeated measurements. If we are unable to uniquely associate a symbol with the manifestation of the property, which is equivalent to saying that a single numerical value and the reference are not sufficient to represent the value of the measurement, then we must conclude that the measurement process can only provide us with a limited amount of information about the measurement. In other words, the measurement process can only provide us with an approximation of the value of the measurement, a value that we will never be able to know with absolute certainty. The question we should ask ourselves is, can we really rely on this finite amount of information about the measurement provided by the measurement process? For example, can we use it as input data in a decision-making process? Or does this entail a serious risk of making the wrong decision? The answer to this question is yes, but only if we are able to assess whether the amount of information obtained is sufficient for the intended use of the measurement result. To do this, we need to delve into the mapping process and understand how and through which steps we come to assign a set of symbols and therefore values to the manifestation of the property we want to measure. It is necessary to define a model of the measurement process that allows us not only to represent the various theoretical and experimental activities that contribute to implement the mapping process, but also to identify where imperfections originate. Let's call them for now in this way, although not strictly correct, which prevent us, through the measurement process, from getting the true value of the measurement. To summarize, we have seen that the measurement process builds a bridge between the empirical world in which the quantities we intend to measure manifest themselves and the world of symbols, that is, the values we wish to assign to these quantities. We have also seen that the values we are able to obtain provide us with only incomplete knowledge of the measurement, and that we must find a way to quantify the extent of the missing information.